NeoBay Robotics Forum is an academic platform launched by Science Robotics in collaboration with the Institute of Medical Robotics, Shanghai Jiao Tong University, aiming to promote the latest advances in robotics and allied technologies, as well as ongoing basic science research and engineering challenges. The online forum is open to the general public and held monthly with speakers from leading research organizations and industries around the world.
So it's really a pleasure today to share with you some of the results of the work that we do in our laboratory. And as you can see in this artistic rendering, lots of the activities of my lab is centered around aerial machines, but not only. But today I will be trying to make a story around flying machines, and so we'll focus on some of the aspects that we are investigating. As you can see in this image, we are interested in bioinspired drones, not necessarily flapping wings, not necessarily insect-like, but in general about we are taking inspiration from nature, from fly again. But it turns out that if you look at flying animals, they withstand collisions and they continue or they can resume flight. How do they do it? So many years ago, one of my master students, Adrien Brio, visited Rob Wood at Harvard, and he came back to EPFL with these video scenes where we can see this insect flying in confined spaces where the walls are like mirrors, and the insect does not detect these walls, bumps into the wall, but sometimes it falls to the ground, but many times it just is capable of absorbing the collision through its exoskeleton. And then the exoskeleton deforms and then goes back into the original shape. We thought, okay, let's try to design a quadrotor that has a similar principle. As the quadrotor flies here, normally the frame must be very stiff, otherwise the drone would not be sufficiently stable to fly. But when the drone, for example, falls to the ground or hits a wall, the arms that experience the contact should give way, should become flexible, just like the wings of the insects. And as soon as the collision is over, they should snap back in place and remain sufficiently rigid to withstand the aerodynamic forces. And so Stefano Minchev and some of our students in our laboratory designed this drone. Here is the concept. The external frame of the drone is made of foam and the PCB, and is very flexible. If you look at the coleoptera wings, the ones that I've shown to you in the previous movie from unfolding, rapid unfolding, we notice that there are two main patterns of creases or folding patterns in these wings. One pattern is so-called, is very close to the body of the insect down here, and is mainly used for folding the wing against the body of the insect. The other pattern is called the tip crease pattern and is towards the tip of the wing and is used to reduce the dimension, the overall dimension of the wings. And so again, my former postdoc, Stefano Minchev, and other students designed an origami wing that mimics or takes inspiration from the folding pattern of this coleoptera and allows a wing to fold in a very complex space. Now you can see that the unfolding is very rapid. This is a slowed down, 10 times slowed down process of unfolding. The wings automatically unfolds because the elastic energy stored in the creases allows all the different parts to spin out, to fold out. But once it is completely unfolded, it is sufficiently robust or resilient to the aerodynamic forces required to maintain the stability during flight. We designed a drone which has morphing wings and morphing tail inspired by the northern goshawk, which is an excellent agile bird of prey. The drone is modeled along the dimensions of this bird, but the important thing I want to show to you is that it can fold and unfold the wings symmetrically or asymmetrically. And by folding the wings asymmetrically, they can change the aerodynamic forces, and therefore they can perform rolling motion, just like birds do, to turn. So they don't need ailerons as airplanes do to do that. They can simply asymmetrically move their wings. They can also symmetrically change their shape in order to withstand headwinds. They can move their tail in order to change the direction or to perform aggressive maneuvers. And I want just to show to you how this happens in this video, where you can see this drone flying in the sky, taking off. And you can see in the inset on your right screen, as the drone flies through in the environment, the current configuration that it has. Now the tail and wings are tucked, so it can fly at very high speed. Now the tail is opened, so it can be used for steering or for air braking. Now we can open up the wings. It allows the drone to be much more maneuverable. You have more aerial surface, or it can turn more agile. So
and I want to start with a almost obligatory video here that just shows you basically what the goal is. And that really is to build robots, machines that feature a lot of the same functionalities that we see in natural soft biological organisms. And so the octopus, of course, is a big source of inspiration for researchers within the field of soft robotics and just more generally bioinspired robotics. And what we see just even in this short clip here is just an extraordinary range of functionalities. In addition to the mobility, we see the ability for shape change and color change, adaptability. And what's really remarkable about these organisms is that they achieve these functionalities. I will say, though, that for the most part, these soft robotic systems, although they're untethered and although they have some of the capabilities of natural organisms, are still way slower than their natural counterparts. If you look at some of the early work, say from George Whiteside's group and Rob Wood with these pneumatically powered quadrupeds, if you look in terms of the speed, in terms of their body lengths per second, they're orders of magnitude slower than natural organisms, or for that matter, even bio-inspired robots that are engineered using more conventional approaches. I'll focus on shape memory materials for two primary reasons. One is that these materials have very high work densities, and so we can generate a lot of force with very small volume of material. And another nice feature of these shape memory materials is that they can be electrically powered, and so we can power them off of a lithium polymer battery, and use miniaturized electronics to control the voltage and current supply. So the one of the architectures that we've adopted, and I'll turn the volume off here, is quite simple in the design. We just simply take a wire of nickel titanium shape memory alloy, we loop it, we sandwich it between two layers of thermally conductive rubber. One of those layers we pre-stretch, and so that when we attach these, the actuator naturally curves. When we supply electrical current, as you can see here, we get this kicking motion that causes this pretty rapid actuator effect. Videos on the left are in real time, and you see that we are approaching close to kind of biologically relevant speeds of locomotion using shape memory alloy. The challenges, of course, with thinking about a physics engine for soft robotics is that these are infinite degree of freedom systems. And for all of you who've kind of worked with finite element analysis, who've had issues with meshing and convergence and long simulation runtimes, it's not going to be practical to be able to do those kind of computations, say on the robot, or for that matter, even in the cloud, in some cases, as this robot operates in unstructured environments. And so what we are aiming to do is to create alternative methods to finite element analysis, where we can rapidly, and in some cases kind of in real time or even faster than real time, simulate the physics of these soft robotic systems so that we can use that information back into the decision making and the planning for these robots. And so this is a test bed that we use to experimentally validate that test bed, that physics engine. I'm not going to go into kind of the details of the physics engine we use, but just in short, what we're doing is adapting techniques in computer graphics. And in particular, we're using practices in discrete differential geometry. So moving on to some other soft robot test beds that we've built using shape memory alloy. In addition to that loop of straight wire, we've also used coils of wire, and this is adapted from a group in the UK. And what this allows us to do is to make these tentacle type end effectors that are actually capable of bending not just within the plane, but actually in and out of the plane as well. And so we've used that to create this Bioinspired soft robot. This is actually inspired by the brittle star, which is a certain type of starfish or a sea star. As you can see here, it's fully untethered. This video is in real time. Again, actuation is achieved with these SMA coils. Create these electrically conductive pathways between those liquid metal droplets. And anytime we introduce damage, what we observe is that the mechanical pressures, those stresses from that damage cause adjacent liquid metal droplets to rupture and form new conductive pathways to bypass those damaged areas. And so in that sense, we get this kind of autonomously self-healing electrical circuitry using our soft materials. So in a sense, this is somewhat analogous to neuroplasticity in natural nervous tissue. So again, kind of drawing inspiration from nature to achieve these kind of autonomous behaviors with soft materials. And so how does this manifest in a soft robot? Well, here's an example of having a microcontroller connected with these SMA-powered limbs, where we use these self-healing electrical interconnects to have that wiring between the microcontroller and the SMA coils. And so as we introduce damage, because of that self-healing effect, we see very little influence on the current that can flow from the microcontroller to those SMA wires. And so